Hey guys, welcome to the video. Today we are going to start off on a new C project here, and we are going to be building out a virtual file system. So I have a graphic here to kind of help explain what that even is and how and what I'm going to be specifically focusing on. So if we take a look, these virtual file systems and file system drivers usually exist in kernel space. Let's say in Linux, these components would be kernel mods in the kernel. But for our case, we're just going to do application. Like I'm not going to make kernel mods for Linux right now. So that's how I'm approaching. These are just going to be C applications. But what I wanted to explain is that when like a user space calls like open or reads, this virtual file system handles that. And what the virtual file system's main job is to abstract away the specific driver. So regardless of whatever driver is trying to, or whatever driver the user space is calling upon, which we would know based on like the file path, if like it's within a mounted path, you would have to know what the driver is that handles that mounted path. But basically, it would abstract away those open, read, write calls where no matter what the driver is, if someone were to implement a driver for a file system driver, if you fit the standard for that virtual file system, the virtual file system will be able to handle all of the open, read, and write calls without making any changes to that virtual file system code, which is great. Makes it super modular. Then you can just fit the drivers to the virtual file system. The virtual file system will just abstract away the specific driver, and you don't need to know anything about it when you want to call open or close or any of the file operations. So yeah, so that's kind of what we're going to do. We're going to be mainly focusing on that virtual file system, and for now I want to implement just the CramFS side. CramFS is just a name I gave to the driver. It's not like a specific driver. It's basically just a RAM-based driver, which means the file system's just going to be in a memory blob in RAM that I will handle. So instead of it being like on disk, which makes it a little more simpler. So we're going to start with that and see where we go from there. We might end up also doing a file system that's on disk. But for now, we're going to stick with CramFS as our first goal. And yeah, I'm going to get to designing implementation a little more, and then I will catch back up with you guys. Hey guys, I'm back to explain some of my design approaches that I'm going to implement. Some of these could change while I'm implementing. It's mainly, most of the stuff I'm going to be explaining to you is how I'm approaching it, kind of structure wise, how I want to organize the data so that I can perform the logic over it. So I have some graphics. This is the first one I want to show you guys, just to help visualize what I'm trying to say. So starting with how to handle our registration of drivers and the mounted file systems and kind of the relationships between those two. So it's pretty simple how I want to handle it through the structure or through the structures I have. So basically we're going to register a driver, and my thought is that a driver such as CramFS would call our VFS register driver and then give us that information. So down here you can see like this function would call, or CramFS would call this, give us the name of the driver, and then give us their mount and unmount functions. I was thinking of doing all file operations here, but there may be file operations that are per inode, since it might be different for directories and actual files with data in them. So I'm gonna just return mount and unmount here, and then store them in this array. So at the top array is where I'd store like the registered drivers. So you can see like CramFS is stored in there, and then we have a file system driver with mount and unmount functions that we're going to get back from that we get from the driver. And then once we want to mount a file system, now that we have that driver registered, we would we would store that in this mounted file system array. So it would be this driver is used in the mounted file system structure that I have here, and it would be with the other file system related data that I need. So the path of where it is, and then the root inode. This root inode will basically be used to iterate through the file system. So that'll just be like the root directory, basically. And then from there, we can move through different things. So this is kind of how I'm thinking of organizing these two arrays to handle these structures. This is the next graphic I wanted to show you guys. It's just a simple overview of the relationship between our virtual file system and the driver, in this case CramFS. So we see that this is the struct for the file, and it'll be stored in the file descriptor table, which is just another array where I'm going to store any of the open files there are. So the flow, as you can see in the diagram here, basically you would do a VFS lookup, and with that lookup you would give it the root node. We get that root node from the mounted file system, so we would have had that mounted file system. We have that root node, and now we want to open something in that mounted file system. So when we go to mount that, we do a VFS lookup on that mounted, or on that file system. We're going to give it the root node to look up off of. So then from there, when we give it to the driver knows how to iterate through its file system. So with the root node, it can find, with the root node in the path that we want, we can then iterate through the file system, find the file inode that we're looking for. So and then it'll return that inode. So after we find the file we're looking for, it returns us an inode. We're going to make a file structure out of that using that node. And then from there, we can perform operations on that file. So the node is going to provide us the file operations. So now we can use the file structure to then perform the further operations we need. We won't have to ask the driver for any more information since we're going to have it stored here. So that's kind of just a quick overview of a few different design implementations of like structures of how to organize the relationships and data that I have. So we're going to get into coding for a bit, and I will check back in. All right, so I got a little bit further along. I set up some logic to do the register a driver on the VFS side. And as I was mentioning in the explanation for how I want to implement things, I would have CramFS call that with the driver name and then the mount and unmount functions, which are right here. So let me go back. Here we go. Yeah, so we have this driver function. It's pretty simple. We just set up a driver. We just set up a registered driver, set the name, the FSD, which is just the file system driver functions, which are mount and unmount, and then increment that count so that if we have to do another driver, we can add another one to the array. I also have some logic for VFS mount. This is just basically untested logic. So this is how I figured the logic will be for mounting, although I can't test it until I implement a mount on this side, which right now you see it's just returning null. Oops. So then we can go ahead and do a quick run. And this is our main. It's just calling the register, so we can just see that the driver table or the register driver is made and added to the table, and we can see that there. So just a little check in here. Next, what I want to do is make a blob generator in CramFS here. So this will just represent the block of memory that our file system actually will live in. This is basically just for examples, and so that we can start doing a little more complex things to our file system that's in memory. So realistically, this blob of memory would be given to be mounted. We wouldn't be creating it from like the driver wouldn't be creating its own file system, right? All it does is handling how to manage that file system. So it's kind of just something I need to do in order to get an example file system for me to work with. So let me do that really quick, and then I'll kind of explain to you guys what I did. Okay, so I'm back really quick just to show the code for how I made the blob, which is going to be our file system in memory. It's basically just hard coding this on the left here, this readme, this file system into memory. When we parse this blob into like our actual file system structures that we're gonna maintain, it will be like in a general way. Like it could have realistically any of this blob, as long as it's in this format, can be parsed regardless if there's way more inodes or way more files, way more directory entries, or whatever it may be. Yeah, so it's basically just hard coding this into memory. So I have these structures that I made. They're packed so that there's no space in between bytes of it. So when I parse it, it's easier to do. So it's more predictable. So it's pretty simple. Just made each block, which is each struct really. So super block, and then I just write it to memory. Do the same thing for the inodes. So if we go back here, there's 4 inodes. So 0 through 3 here. Write those into memory. There are 2 directory entries, which we just write into memory, and that's fine. And then we write the actual data at the end there. So it's pretty simple. We can see, yeah, so this is just basically we see the magic bytes, a number of inodes, which we know is 4. The directory entries are 0 and 1, 0 and 1, and then their children, the amount of children for each is 2 and 1. So 2, 1, and 3. So yeah, so it's just to show that this is the memory file system block that we're expecting. And then from here, we will make a function to parse it. Again, realistically, we wouldn't be building our own blob. This would be given to us. But for testing and stuff, we need to build our own blob. So this is just a good thing to have here. And I can always just change up the format or to resemble different files or different inodes, different directories, whatever we want. So I will implement the parsing of this blob, and that's where it'll get a little more interesting since we want to make our file tree and everything. So let me get to that, and then I will update you guys then. Okay, so here's the code for parsing that blob. I think I will have to change up how I make my file system blobs eventually. Right now it's kind of like a static image I'm reading in, but that makes it a little hard to dynamically make things. I think I could do dynamically making files and writing to files so it changes like the amount of data. I would just have to rewrite it all into memory. or yeah, rewrite it into another blob. So it's basically like recreating the file system from scratch. So I don't know. I might have to do more with that, but for now we're just gonna read this in. So this is our parsing that file blob code. We have um, file system tree node root up here. So this will just be a global variable to store the root of our file system, and that is basically going to be this structure. So it's just going to be the node, the number of children the node has, and then pointers to the children. If we scroll down here, okay, so we parse out the super block. The super block should be the same over both. So we're gonna parse out that super block. We're gonna pull this over here. We're gonna parse out the super block, get the inode table offsets and directory table offsets and the data block offset. So this will to get us pointers to all the like arrays that we want. Where are we? To these. So we want pointers to all these parts that are allocated within that memory blob. So now we're gonna have pointers to that. So I just offset them from the start of the blob. So now we have pointers to those different parts. And this is where the main code is. It could definitely be cleaned up more, like creating inodes should probably be moved to a function. So I'll probably do some of and like parsing out a super block could be moved. But for now, this is just simpler. So we're just gonna go with this. So pretty simple, we're gonna pull out an inode. So the directory table, if we go back to here, right, so we have a directory table. We're going to pull out the inode ID. So let's say for this one, it'll be 0. We're going to pull that out. We're going to get the pointer to the inode that it's pointing to. So since it's inode 0, we're going to jump into or go into the inode table and pull out the first one. So now we have a pointer to the start, or we have a pointer to the inode we want. Then we're going to get the number of children, which is just the number of children from the directory entry, and start setting up a tree node. So we have two cases. One is if the root's not null, so that means we already have a tree filled out. And then otherwise is when we would have to set up our whole root to begin with and then ultimately get to here. So on first iteration, we would go through here since the root is null to start. Pretty self-explanatory. We're gonna fill out we're gonna fill out an inode. So we're just gonna fill out this structure. All the information for the structure is in this inode table, right? So we have, since we got a pointer to that inode we want, we can just pull out all that information. The only thing it doesn't have is the pointer to file operations, which we have from here. So we don't really need it to be in the file blob because it doesn't make sense since the pointer only would be relevant like in the context of when I made the blob, so it doesn't make sense to store it. So basically we set up this inode, come here, and we set up the tree after, or we set up that node after. In this case, this would be the root node. So we just set the node, set the number of children, and allocate space for the number of children, which is just allocating space for a bunch of pointers, in this case 2 pointers, since the directory entry that will be the root here has two children. Then we get into here, and this is where we loop to make the children. So this basically just sets up same thing. We're again just gonna fill out these nodes, but we're just gonna fill one out for every child that the node has, and then set the children equal to that, and then we're gonna move up this directory entry. So after first loop, we're gonna get to this directory entry now. We're gonna go back up, and now we're gonna go in here since we have a root now. Once we're in here, we're gonna find a parent. So if we are trying to get, or the directory entry will be a different node ID. So if we're looking for since the next directory entry is the next one down, we know that if the root's there, we know that inode for the next directory entry must exist in the tree already. So basically that's what we're gonna do. We're gonna find the next parent basically. So in this case, we're gonna find the parent because we know it's a child of the root, or a child of some other directory entry that may have came before it, which is in this case would be the root. So we're going to do find parent, which is down here. We can take a look at. So it's pretty simple. It's just a recursive function. If the number of children is equal to 0, we're going to return. So that's our base case. We want it to return if there's no children, because that means that we can't loop through here, right? We know if that node ID is not it, then there's no children to check. So we can just return from that call, that find parent call. Otherwise, we come into here. So we check for the number of children, we loop through the number of children, and then we just compare the ID against it. And if the ID is not equal, then we call our function, recursively call our function with the child node. So basically just that first search is through the tree to go through all the children in order to check for that ID, and then eventually if the ID matches, then we can return from that. So now we have inode 1, right? Because inode 1 was a child of inode 0, this directory entry for root. Now we have that. We have the tree node that was already created for it. Now we can set the num children and then allocate for that, and then we do the same loop here and build the children. So in this case, it's only a few loops through, and then our case is basically if we hit the data block pointer, since we know data, the pointer for the data is after the directory entry arrays. So if we hit that, then we know we're out of directory entries. And then we just return the root node. Okay, so now we can look at this diagram to help visualize like what our tree would look like with this file system when we're parsing that blob. So we just see root 0 here, and then we go to node 2 on the left, which is the hello.txt, doesn't have children, and then we go to node 1 on the right, or in the diagrams on the right, and that is a directory, right? So then that has children, has one child, and then so when we grab node 1, when we do that find parent call, node 1 we know has a child, so we're going to set that, and then we have the readme at the bottom, and then that doesn't have children. So that would be the end of our file system tree. That would be the end of the file system tree for that. Okay, jumping back, we can kind of do a little sanity check here. So I just have the parse blob here, and then I do a print tree, which is just a function similar to just same thing we're doing to find a parent. We're just going to depth first search through it and print every node we see. So we can go ahead and run that. Okay, so this is what we expect, right? So 0 is the root node, then we have 2 and 1 as children, and then 3 is the child of 1. So that's kind of what we expect to see, so that's good. And yeah, so this will probably be the last piece I'll do for this video, and do another part to implement the file operations on it, since this was a little bit of a larger lift, this and the creating the blob and everything. So I will see you guys in the next video, and then we can start implementing all the file operations and actually test mounting and all of that, since we haven't had a chance to actually test all that. Now that we have the file system here and we read that in, now we can do actual more complicated operations on that file system. So yep, I will see you guys in the next one.